from Cătălin Hriţcu. It's a researcher, director of research.
Not yet.
Not yet. Close. He's a researcher at Inria in the group Prosecco. He's mainly in 3 projects, if I remember well, plus a 4th. So in FStar, he's one of the main developers of FStar. There is the project SECOMP on secure compilation and hardware enforced security policies, among which security. And he says that he doesn't do any more quick check, but actually, if you ask kindly, he's going to go. So today we're going to have a presentation of FStar. The floor to Cătălin.
Thank you for the invitation. So yeah, Marco worked with me for a while on secure compilation. But what I'm talking about today is verifying effectful programs in FStar. So it seems like a fairly informal crowd. You can ask me questions. I have quite a few slides, but I don't plan to go through all of them if we discuss. So I'll start by explaining that the FStar is a large team project. There's about 20 people or so currently contributing to FStar with different levels of involvement. The main designer and developer of FStar is Nick Swami. It's a project between Microsoft Research and Inria and also people at in other places. So yeah, it's not just my work. And in a way, there are many different schools of formal verification out there. And FStar tries to bridge the gap between 2 of these schools. On the one side, you have interactive proof assistants like Coq or Isabelle or Lean that are very successful. Things like ComCert or 4 Colors or SEL4 have been verified in interactive proof assistants. They have very expressive logics, higher order, dependently typed. But I would say they're the best for purely functional code. And well, you can do more work to do other things, but I would say the things that they shine is if you can write your whole compiler or something like this as just a purely functional program, like Xavier did for ComCert, then that's the best situation for using these tools. On the other side, you have tools that are meant to reason about imperative programs. Tools like Daphne or Framassi and Y3. And they work in a quite different way. They work by gathering large verification conditions and feeding them to SMT solvers. The nice thing is that they reason about programs with effects, like state and concurrency and you name it. And they have good SMT-based automation. The not so great thing is that you're usually restricted in the kind of specifications you can write. You're usually restricted to something like first-order logic. And also, in a way, you're restricted when all this automation fails. It's not too easy to then still complete the proofs. So FStar is trying to bridge this gap. And it's 3 things. First, it's a functional programming language with effects, like OCaml or Haskell. It can be extracted, in fact, to OCaml or F#. And the subset of FStar can be compiled to efficient C code. So if you program in this low-level fragment of FStar, which in a way is an effect, I am going to talk about effects, you can extract your programs to C. Then, well, FStar is a program verifier based on gathering weakest preconditions, computing weakest preconditions, so large formulae that get fed to an SMT solver, like Daphne or Framassi or Y3. And when that automation fails, FStar is an interactive proof assistant like Coq. So you can still do your proofs interactively and I'll even talk about support for tactics. So you can do tactic proofs, say in the style of Coq. And yeah, maybe I should mention that the goal of F-star is not to replace OCaml. We are compiling to OCaml, in a way it's complementary. It's also not to replace Coq. If your problem fits into this purely functional programming style, then you're probably better off using Coq. However, if you want to have this SMT automation and if you want to have these three things all in one, then I would say that then F-star becomes a good tool.
Where would you fit Idris in this picture?
Right. So there are other tools in this space. One of them is Idris. There are more. There is something like CoqHammer, which gives you just an SMT solver to solve Coq goals. So there are other tools in this space, and they're all fine. They all have a different mix of these things. I would say F-star is the one that best puts together all these three things. In particular, yeah, the thing with the SMT solver, and you won't get that in Idris, for instance. And I won't talk a lot in this talk about how to scale F-star to large things, but I will just give you some examples to impress you, and then you'll believe me that it does scale, at least to this extent. So as a functional programming language, we use F-star to program itself. So F-star is programmed in F-star, but not verified. In a way, it's just to see that, hey, you can write interesting programs in F-star. And it already shows that, for instance, the Coq people don't write there. The Coq is not written in Coq, unfortunately. So in a way, it does show that these effects, having effects like you have in ML, does help to write more efficient and better code sometimes. As a program verifier, I think here we have the most convincing case studies. In Project Everest, where we are working on verifying and deploying a complete HTTPS stack. So this includes MeTLS, which is the verified implementation of TLS. This includes Hackle, which is a verified cryptographic library, and this includes which extracts to C, and I'll say a bit more about it. And this includes Veil, verified cryptographic algorithm at the assembly level, because sometimes for certain algorithms, in order to get the best performance, you cannot stay at the C level. The hardware just gives you, say, an instruction or some instructions to do AES. And if you don't use those instructions, your software implementation will be orders of magnitude slower. So you really need to use those instructions sometimes. But for many algorithms, the C implementation is fine. So you just use the Hackle one. And then as a proof of system based on dependent time, well, for dependent types, we really see this mostly as a fallback when SMT automation fails. But we still have certain case studies. We have a fragment of F-star that was formalized in F-star at some point. We have a domain-specific language for secure multi-party computations, a variant of Wisteria you might have heard of. And some people did a verified compiler for reversible circuits for kind of quantum computation. It was some other team at Microsoft that almost independently pulled this off, despite the challenging of using, at that point, a fairly immature tool. So we have this. I'll zoom in on Hackle, which is this verified library implementing modern cryptographic primitives. It's written in this low-level fragment of F-star. It's extracted to efficient and readable C code. And because this code is efficient, readable, and verified, and I really put them in this order because that's what people in the real world care about. Then it got really deployed in places like Firefox. Their NSS library now uses increasing amount of primitives from Hackle. In Wireshark, which is part of the Linux kernel, and it seems that there is a wish to revamp some of the Linux kernel cryptography in general, because there are many cryptographic algorithms in the Linux kernel that have very ad hoc implementations at the moment, and there some people are pushing to switch to Hacklestar beyond just the Wireshark, which is this tunal protocol, like some sort of IPsec kind of protocol. And other places, I guess it's in WireGuard. Sorry, yeah, yes, my typo. I guess it also includes this list also includes Tezos, or might include Tezos at some point. At least that's what I heard, that there is interest in using Hackle as well. And yeah, this is developed mostly across the river at Inria Paris by Karthik and Benjamin and some other students there. So if you want to hear more about it, you should invite Karthik, and he will gladly tell you about all the successes of Hackle and all the other places where it's getting deployed. When preparing for this talk, I also found out that one of the people in the FSTAR team, called Santiago Zanella, has been working with Thomas Ibupinot on an interpreter and program logic for Michelson, and they weren't too far of completing this project. And what Santiago told me, beyond that, yes, I should advertise this to you, he told me that if anyone here is interested in helping him complete this project and collaborating on it, he would be super happy to return to it. Because otherwise there is nothing published about it as far as I know, so it would be nice to get this out there. The other thing I've heard recently is that Marco is working on a little prototype for the economic protocol, or just an implementation of a little economic protocol in FSTAR that extracts to OCaml and runs at the moment. So it seems like there is some interest, at least in trying out FSTAR. Now, I won't be telling you more about it in this talk. What I'm going to do is really step back and explain more about what FSTAR is. So explain about the functional core and how we verify functional programs, and then about monadic effects and how we verify programs with effects. And then, if time permits, explain to you a bit how things look like under the hood, how we compute these verification conditions, and how we do that in a way that's independent of the particular effect you're working with. So this, I'm going to now step back and explain everything with extremely simple example. It might look a bit toy. You should remember that yes, this thing is real, and we have interesting case studies, but because I have to go through, or I would like to go through quite many things, I thought that it's the best to use simple examples, really simple examples, toy examples. Questions so far? If not, well, I'll press on and explain about the functional core of FSTAR. It's ML. At the base of FSTAR, you have just the normal functional programming you guys are very much used to. You have recursive functions. If I wouldn't have told you that this is FSTAR, you would have thought this is OCaml or something else. We have inductive data types, where our syntax for lists is a bit better than in ML. It's more like in Coq, but other than this, map is really the same as you would write it in ML. And lambdas, well, okay, no surprise. So it's really the usual functional programming you know for a start. Where things get more interesting is at the type level. We have more expressive types than just in ML. And the simplest example is we have this thing called a refinement type, where we say that x is an integer, but it should satisfy this logical constraint that it should be larger than 0, and this gives you the natural numbers. So we call this refinement types. And now if you take the same code, the code of factorial, and you snap a type annotation saying that this is a function from natural numbers to natural numbers, then now F star can verify that this code indeed, given a positive number, produces a positive number. The code hasn't changed at all. And in fact, these refinements are introduced by these type annotations and eliminated by subtyping. So there is no extra construct in the code to use these refinement types. However, to type check this program, you already have to do some verification. And just to give you an idea, the kind of verification conditions, much simplified, that get fed to the SMT solver in the end for this kind of code is something like this. So once you have to verify that this call on factorial n-1, this n-1 is really still positive. And well, so it's this part. And you know that it was, that n was positive. And additionally, we've branched whether it was 0. So it wasn't 0. We took that branch. So we know it's positive. We know it's not 0. So n-1 is positive. This is a very simple thing for an SMT solver to prove. And the second one, well, we have to show that 1 is a positive number, and that's very easy. And we also have to show that this multiplication is as well positive, knowing that n is strictly positive, and knowing that the recursive call is going to return us a positive number. So this is, again, very easy for an SMT solver to prove, even if there is, in the end, this is nonlinear. But at least Z3 can prove this. It's not a problem. Now, yes, questions?
What about overflows?
So I didn't explain what the type int is, but it's the type of infinite precision integers, of mathematical integers. So we don't, if you want, F star also provides bounded types in which you could either wrap around or you can enforce that you don't overflow, and we do that. But well, in all my talk, I'm just going to use int and not as the only two interesting types. But you can imagine that in the same way I define not, I can put also an upper bound on this thing, and I'm going to get a bounded number. Okay, so the other thing, which this code, I'm not sure how much it showed, is that when you have say a natural number, you can also use it freely as an integer. And this is just by subtyping. You don't have to do explicit coercions or anything like this. So in a way, these refinement types differ from these sigma types in Coq, although it's the same idea, but without the coercions. The other thing that should also be quite standard from Coq is dependent function types. So we can give a name to the argument of the function, and then refer to it, say, in a refinement that we put on some other argument. In this case, I'm saying that increment takes x, which is an integer, returns y, which is an integer, and ensures that the thing it returns is larger than the thing it got in. So in a way, we can already express some notion of pre and post condition for pure functions with just these dependent function types and the refinements. So that was already a perfectly fine specification for increment, but I might want to give a more precise one, in which case basically I've lifted the body of increment to the specification level. And I can do that because, the body of increment happened to be pure. So it is its own specification if you want. And in fact, if I wouldn't have written any annotation, then this is also morally the type that F star would have inferred anyway. It does infer the weakest precondition and stuff like that. I'm going to get to that much later in the talk. So yeah, this is again not super fancy. But yeah, the reason we were able to lift a computation to just act as a specification was that it was pure, and all the functions we've written so far are in a way total. And the default effect in F star, well, I didn't write it, but when I wrote not to not, actually F star by default will try to prove that that's a total function. So in fact, the verification conditions I showed you weren't all the verification conditions, because there are also some verification conditions required to prove that this thing is total. And actually, if I wouldn't write this type annotation, I didn't show you, I mean, I showed you the code, but I didn't show you what would be the type that F star infers for it by default, is actually something that's like this, just by type inference for that code. However, if you try to give factorial written this way, this type, F star will complain, and you can imagine why, because this function, when called on a negative, when a negative number, this function loops, because the check is just for 0, not for negative. And the kind of error message you get in this case is the subtyping failed, that it was expecting to get x which is smaller than n, but well, it just got an integer for, well, this n minus 1. And you might wonder what that smaller than is. So F star has some we call it a semantic termination check, that's based on this well-founded ordering on expressions. On natural number, this is what you would expect, is smaller than. And the negative numbers are unrelated. You could relate them by larger than, but then it would be odd. At least people will be surprised. Then for inductive types, for lists, you have the usual subterm ordering. However, there is one special inductive, which are these lexicographic tuples that get lexicographic ordering. So these are the only, well, okay, there is a fourth case, but there are very few cases for this ordering. And this order constraint are discharged by the SMT solver. SMT solver knows very well to work with integers, and we axiomatize what it means to have subterm ordering and lex ordering. This is easy. And well, then, and this is the baseline. But then you can write your own decreases matrix. Decreases matrix. So if you, I don't know, you have the Ackermann function and you want to tell F star that, hey, Ackermann decreases on a lex tuple with the second argument first and then the first argument, then you can do this. And it's not very common that you have to write this decreases cost, but for fancy functions like this, you have to write them. And well, this is basically any pure expression, you can write it in there. And in fact, this kind of lexicographic ordering of the arguments, but in the order they come, is the default in F star. So if you take all function arguments and you order them in lexicographic ordering, that's the ordering F star gives you by default. So if I would have swapped the arguments, if I would have put the m before the n, then I wouldn't have even needed to write an ordering, even in this case.
I suppose that aside from termination, you can also give some indication about the complexity of
No. So one can think about this, but yeah, termination in a way it's something that's kind of hard coded into the system because we want to have this pure fragment. One can one can think about, well, doing complexity analysis or this kind of things, say using the F-star effect system or keeping track of gas or of something. But that would be something you would do on top of the basic system. More questions? So, well, you might not want to prove all your functions terminating. For instance, the factorial function we originally wrote, well, can still be type checked as an int-to-int function, just with effect it possibly diverges. And in this case, it actually diverges on some inputs. And this is not just, well, because we are lazy and we don't want to prove termination, but some useful code really doesn't always terminate. If you're writing an interpreter and your language for which you're interpreting is Turing complete, then yes, the expected behavior is that on omega, say this is the small interpreter for the untyped lambda calculus, and this is omega. If I'm evaluating omega, I do expect this thing to loop. And that's the expected behavior of this code. It's not that I'm lazy, I don't want to prove it terminating. So then, well, I can give this code divergence effect, and F star accepts the code, basically turns off the termination checking. And if you run this code on omega, you'll wait a really long time. So F star has this effect system that, well, encapsulates effectful code from pure code. Pure code cannot call divergent code. If you try to do it, if you try to say use this factorial with the div effect inside the type, then F star will tell you, no, I expected, well, got an expression with effect divergence, expected a pure expression. So it doesn't take that. However, in the other direction, if you have a pure expression and you need a divergent expression, potentially divergent expression, well, it's completely fine. And there is a notion of sub-effecting that allows you to go from total to divergent, to potentially divergent. So if you write, I don't know, increment, which was total, plus factorial, which was divergent, well, you get a computation that is divergent. And in this case, actually diverges. So this is just, again, happens by, in the same way for value it happened by subtyping, this happens by sub-effecting. So, okay, in terms of verifying pure programs, there are a few ways in which you can do this. I guess the most common way is intrinsically. So you basically prove properties of program at definition times by giving them strong types. In particular, well, when we gave factorial this strong type, we were doing already verification. In fact, you can write the specification of factorial also in terms of pre and post conditions. So instead of using refinements on the two ints, you instead, well, use a different variant of the total effect called pure that in addition takes a pre and the post condition. And the precondition says that the input should be larger than 0. The post conditions say that whatever the result is called y, it has to be also larger than 0. And so in a way, we have these computation types, things like pure and div and tot, that first explain the effect of the computation, second explain the type of the result, and third, well, in the case of pure, they take the specification of the computation, and I'm showing to you and as to most users this specification in terms of pre and post conditions. But in the end, I'm going to show you that these are in fact the sugar to just very weakest precondition predicate transformers. And well, okay, yes, tot is really can be seen as an abbreviation of pure with the true post condition and the true pre and post conditions. And we can do the same thing for div, and here is more interesting. In particular, well, I can give factorial type div. That's not too interesting. But in a way, I'm capturing some sort of partial correctness. I'm saying, well, okay, I should have written, okay. Here is a more interesting example. I can give this evaluator for lambda terms. I can give it a partial correctness specification. I can say, well, if you give me a closed expression E, then I'm guaranteed to give you a closed expression E prime out, and this thing has to be a lambda. Because, well, it's a value in a way. That are the values of the n-type lambda calculus. So this doesn't tell you that this computation is terminating. It cannot. But it still gives you useful information about what it's going to produce if it terminates. And then the code is almost the same as before, but there is this additional call to a lemma that, well, is proved somewhere above, and I'm going to explain lemmas right on the next slide. But there is this call to a lemma that's kind of computationally irrelevant. It returns a unit in a way, but that helps me prove the specification. So here you already see some amount of verification of effectful programs, although very simple. Another thing you see is that I didn't have to match on the variable case because I have a closed E there. So pattern matching as opposed to incoc is also the exhaustiveness check is also semantic and also kind of done with the SMT solver. So if you know that this thing is closed, there is no variable case. And the SMT solver can figure that if you don't write a variable case, this is still exhaustive. So this is another niceness you get. Also here, I guess, when I called eval closed, I only had the lambda case. I didn't have to write app case or var case because I'm returning a closed expression. So I even know it's a lambda. So yeah, this notation is really a tester. It's checking that it's a certain constructor. It returns a boolean. Okay, questions about this? And then, okay, the dv I showed you before is again just an abbreviation of a div with trivial pre and post conditions, so nothing interesting. So another way to look at this is that F star has two classes of types. You have value types like integers and lists and things like that. And then you have computation types, things like tot t and dvt and pure t pre-post condition, and those are computation types. And the dependent function types in F star are of the form a value type, an element of a value type called x goes to a computation type. And the reason for this is F star is not completely called by value, but it does enforce that the effects are sequenced, what I would say, the right way. That the effect of the argument happens before you call the function. So it's the closest thing to ML you have in this dependent. In a way, in the pure fragment, F star can evaluate in whatever order it wants because it doesn't matter. But however, as soon as you have side effects, the side effects will happen before, say, function calls. So it is strict in this sense. And we see this as a feature. And also this explains why I only write a value type. Yeah. The thing that we will get into your function is just a value. And then we have two forms of refinement types. The usual refinement types are refinements of value types, like NAT. And then this thing with pre and post conditions, or weakest precondition, or blah, I will show you later. These are refined computation types. So in a way, we are characterizing, well, which computations can this expression produce, like the body of the function in that case. And at this point, in a way, the expressive power of computation types and value types for the pure fragment is quite similar. Because I showed you can write factorial with nuts, or you can write it with pre and post conditions, it's the same. In fact, the two are different. And with these refined computation types, you get more power as soon as the effects get more interesting. And I'm going to show you, as soon as you have a state around, the pre and post conditions can talk about the state, but the value refinement can only talk about the values. So it already becomes more powerful to be able to talk about the states. And in the other way, actually, there are certain things you can do with refined value types which get awkward to do with computation types. You can, for instance, have a reference to a NAT, and this is going to ensure that whatever you can only write NATs, and you will always be ensured to read NATs out of it. It basically captures some sort of invariant, or you can have a list of NATs, and you will always know that you have this invariant on the list. You can also do this with refined computation type. You have to thunk. So basically, you have to say, well, this is a function that returns always something positive, and you write a function into your reference. You can do it, but it's up to an encoding, right? So that's why it's nice to have refined value types also in the system, so that you don't have to go into these encodings that might be inefficient and also inefficient for reasoning. Now, if you have a function in my reference, do I have to prove that this is a constant function, that it's not a function that gives me different things? So in a way, I think the easiest is to just have both these things around, and they have a nice duality to the value types and computation types at the normal type level. Okay. So questions so far? So there's a few more ways in which you can verify pure programs in F star. And I thought I would show you this because, well, especially for Coq people, at least this one is a bit new. So it's another way of doing lemmas. And it's exactly the same kind of lemma I used in the middle of my evaluator to just get some logical properties in. Here is a simpler example. I have the append function written as if you would write it in Coq or ML. It appends to lists. And then I have a function that takes any two lists and any type, returns units, so computationally this function you don't need it, right? It doesn't produce any useful result. However, logically, it gives you an interesting fact about the length of the append being equal to the sum of the two lengths. And in a way, you can see it as a lemma, right? This is a for all types A, for all x's, for all y's. I'm proving to you that the lengths and the append are related in this way. I'm proving it after the fact, right? I'm not polluting the definition of append with the fact about lengths, because why would you do that? It seems odd. But, well, I'm proving it after the fact. However, I still have the support from the SMT solver and things. In particular, if I were to just put unit as the body of this function, then basically the SMT solver will try to prove that fact. Now, in this case, it will fail because this simple fact needs induction, and the SMT solver will not do induction for you. So what you have to tell it, more or less the only thing you have to tell it is, this is proved by induction on, I don't know, the first list, right? And basically this is what the skeleton is saying, is say, well, case analyze this first list. If it's nil, then just return unit, which means let the SMT solver figure it out. And in this case, well, the SMT solver will figure out that the append of an empty list is y's, and length of y's is equal to 0 plus length of y's, and that's super simple to figure out. So the only thing that was interesting here was that we allow the SMT solver to compute a bit, so that, well, it figures out that length of the empty list is 0, and the append of the empty list and y's is y's, as you can see from the code. So in a way, this limited unfolding. But then, well, then it's just very basic arithmetic. And similarly here, well, we're only telling him, well, apply the induction hypothesis, but, well, we're not telling it what comes out and how you fill the pieces. It can figure that out for itself. So this is another kind of lemma that you can have in F star, and it's quite useful.
But you use the same kind of syntax to prove the lemma and to write the body of the program, isn't that confusing? I mean, on the first example, you are computing something. On the second example, you are just passing something to less than.
Right, and you can see it in the type, right? That it's unit, right?
You could you could use like syntactic sugar and have a keyword, the lemma.
Right. So we have a keyword lemma that takes this thing and really just writes the useful part. We don't yet have a keyword for removing this boilerplate, although I think we should, and I think with tactic we can synthesize that boilerplate as well. At the point at which this lemma was introduced, we didn't have the boilerplate yet. The tactics.
Another point is, could you have like a function that would compute the length and with the post conditions?
Sorry,
like
we have a function that computes the length.
no, sorry. I mean an append function.
Yes.
Like instead of writing append and append length, you write only append, and then you have on the post condition that append. And the length of append is the sum of the...
Right, so that's what I said I didn't want to do, right? Why would I pollute the specification of append with something that is about the length? This seems super specific, right? And there are many cases in which it's not enough. I mean, in this case, it happened that the proof here really follows the structure of append, but in general, that's not the case. When you just do mathematical proofs, you might need many lemmas, more than just the structure of append. Okay.
Yeah, could you actually abstract away the body of the lemma? Could you abstract this to a separate function? Like, every time you have a lemma that involves just specifying the recursive pattern or recursive first argument or something like this.
Right. So you mean some sort of induction principle? Yeah, I guess you can also.
It to another function.
Right. I guess you can also do that. I guess another thing you could do is abstract away this boilerplate using a tactic.
I mean, a lot of them will have the same shape.
Right. Yeah. I think we have these mechanisms. I'm not sure whether all the pieces are right there worked out, but I don't think it would be hard. Because in a way you're saving 3 lines. Yeah, it's not. It's a constant 3 lines. Maybe we should save them. Yeah. And then, well, okay. You also have the usual Koch style kind of proofs. So I won't go in details, but this is the proof of progress and preservation for simply typed lambda calculus, written as a proof term. And you can write them. In fact, the proof terms look much nicer than in Koch because we have this, as I explained, that I don't have to write all cases. If I know that something is well typed in the empty environment and it's not a value, then I know that it's an application, for instance, and I only write the case there. So it's, if you want, it's still as painful as writing proof terms, and now we have support for tactics, so you don't really have to write this by hand. But even if you write them by hand, it will look a bit nicer than in Koch. Okay, so just to wrap up this part about the functional core of F star. Well, it's a variant of dependent type theory. So you saw lambdas and dependent functions and inductives and pattern matches, and we have universe polymorphism. So you could say it's a dependent type theory, although it's a bit non-standard because, well, we have this semantic termination check for recursion, and we treat non-termination as an effect. We don't completely say we don't want to have effects in our system, but we say, well, if we are going to have them, they're clearly separated from the pure part. we have this refined value and computation types, where the things in the formulas in the refinements are kind of proof irrelevant. Because they're discharged by SMT, that doesn't really, at least the tree doesn't produce witnesses of any sorts. And in general, what you want is this part to be proof irrelevant. In particular, whoever worked with sigma types in Coq, as soon as you also want to work with equality, unless you move to setoids, it's all a mess. And well, then you can just assume this axiom of proof irrelevance, and everything starts becoming a bit more decent. But here it's kind of baked into the system. Then we have subtyping and sub-effecting, which means we don't have coercions to get rid of the logical refinements. And equality is kind of extensional. So type conversion in a star is also done by the SMT solver. Or well, it's done by some heuristics, but then in the end, if those fail, it goes to the SMT solver. Which means, if you have a type equality in your context, it's going to be used to, for instance, to prove the exhaustiveness of pattern matches or this kind of things. So this is for the pure part. I guess I need to speed up a bit to also tell you about effects. So the main idea behind how star does effects, you already know if you heard about monads. It's monads. So if you want to define the state effect, you define it as a function that takes a memory and gives you back a result and another memory. So this is the vanilla state monad. And then you write really a return, a bind, a get, and a put in the usual way. And you tell F star to generate a new effect based on that monad. And the only thing that's a bit fancy, I don't think you have to read it, it's completely standard. The only thing that's a bit fancy is that I parameterize this, at least in F star, this monad is parameterized by the type of heaps or memories you want to use. And for this talk, I'm going to use NATS. So I'm going to keep it extremely simple and say there is a single natural number as your state. In real F star, we have the ML heap or the C stacken heap as the memory model, and that's a lot fancier. But in particular, it's fancier because, in that case, the monad is really used just as a model of how state works. But under the hood, that is compiled to the primitive OCaml heap or the primitive C heap and state, not to just some state passing. However, if you write your own, say, new effect which just has a natural number in it, then this will be compiled to state passing, which is, in this case, is completely fine. So then you can define a larger effect that includes state and exceptions. So you can say, take my now I'm saying it's just a natural number, and I'm returning the final state and maybe a result. So this is the variant of the state monad that keeps the result even if you have an exception, which is the usual one, I would say. I'm going to show you also an example of the less usual one when we do tactics, because that needs transactional state. You want to revert the state when a tactics fails. And then, you have again completely standard code. The only thing I wanted to show you that's interesting is you can define state to be a sub-effect of state and exceptions, and define a lifting between a computation that only has state and raises no exceptions. So you're just going to go left inler. So it's again standard. The nice thing is that, then F star is going to insert these lifts for you. You don't, as opposed to Haskell, or you don't have to write these lifts by hand. In a way, because of this sub-effecting, it's going to be treated by subtyping. So if you use this very simple state monad to say get the state, increment it, get it again, and assert that it got incremented. I don't know. It's a silly example. then there's a few things that happen under the hood. One is that the return and the binds are hidden. You don't have to write return and binds. You write ML-like the direct style code, but under the hood, at least morally, you can imagine that there are return and binds. The ones I wrote here. That's the semantics of this code, right? It threads through a state. But you don't have to write it. You don't see it. You never see this kind of return binds. You also don't see the lifts. So if I write a program that, well, assuming that division requires you to pass it a non-zero argument, and checks whether you pass it a non-zero argument, if it's non-zero, does the division and puts it back in a divides the thing in the reference by x and then puts it back in. I don't know. It's a silly example. Otherwise, it raises an exception. So this code has both exceptions and state. So it lives in this state action effect. And well, what happens under the hood is that, well, there is not just a bind being introduced by f star. There is also a lift. So the then branch has to be lifted from just state to state and exceptions. And f star, well, basically infers the least effect of each computation. And when that effect is too low, well, it just lifts, automatically lifts. So that's what's happening. And you can use this to verify effectful programs. And in this case, well, I would say most of the time you're going to work in this intrinsic style with pre and post conditions, because that's the more powerful one. So here is the increment, or some variant of increment again. So it gets the state and puts back x plus 1 to it. This thing has no preconditions. However, it has the post condition that the final state, n1, it's a natural number, is equal to the initial state plus 1. And I can relate the initial and the final state using these pre and post conditions now. Okay, so this is not too fancy. It's a very simple example. But yeah, it's already more than what you can explain, what you can do easily with this value refinement. Yeah, because I was explaining there is this relation between the states. And this is a predicate on states. And in general, the fancier the effect, so I'm not showing you the state for an exceptions kind of pre and post condition you get, but you can imagine that the result you get in between, which here is a unit, so I didn't write it, would be an option, right? So you can reason about, well, did I have an exception or not? So the fancier the effect, the fancier the pre and post conditions become, and also the harder the verification effort becomes. So in a way, by having more effects, you gain in efficiency maybe, but you do lose in, well, how easy it is to reason about your code. So if you can stay in the pure fragment, well, you should try as much as possible. And then, well, whenever you need imperative code, well, you write it imperatively, but then, well, the verification becomes trickier, harder. You have to start talking about invariance of states, about you raising or not exceptions, about all this stuff. There is another style of verifying effectful programs in F-star, and I guess I'm going to just skip this. But the main idea is, if you've proved your code terminating, even if it's effectful, you can still reveal the underlying monadic representation and still do proofs as if you were in Coq, which is not surprising, I guess, right? And when you do this, I mean, when would you do this? We have some examples. I mean, if you want to prove anything like information flow control, which are properties of more than one run of a program, it's not easy or possible to do just with pre and post conditions that talk about a single execution. You need to relate two executions. Or if you want to prove program equivalence, when you have two different programs and you are trying to prove that, I don't know, maybe they're equivalent in some cases. The easiest is to do, well, to really reveal what they are and then prove a lemma after the fact about their reification. That's how we call this revealing the monadic structure. Okay, it works quite well, but I won't go into detail. Maybe a better example of what we do with effects in F-star is tactics. Because they were defined after the fact, after the system, as I explained it so far, was in place. And it's really defined as a user-defined, non-primitive effect. So this idea that you can write tactics in the language itself is not new. It's for instance what Lin and Idris do. Also, there are some experiments in Coco like MTAC. So these tactics have access to F-star's proof state. So it's a state monad of sorts. But additionally, they can introspect on F-star terms and produce F-star terms in some sort of deep embedding. So there is an inductive type that represents F-star terms, not necessarily well typed. And you can consume and produce. Tactics can consume and produce those kind of quoted terms. And tactics can be either interpreted by F-star's normalizer, which is quite slow, but they can also be compiled to a camel and dynamically loaded back into F-star as native code and running alongside the F-star interpreter that's also extracted to a camel. So this is something Victor worked on. This kind of dynamically bringing back in the tactics with better efficiency. And when you can do that, well, that gives you the maximum speed because they run as if they were native, as if they were part of the F-star type checker. And yeah, the nice thing is that we could do this without greatly extended F-star. In particular, the tactic itself is just a new effect with, well, this, I don't know, the proof state to result, where result is just defined there. It did a success, which gives you a value in the proof state, or, well, failed, which gives you an error message and the proof state at the time of failure. This is the other kind of state and exceptions monad, the one that rolls back the state when you fail. But other than this, I mean, it's just another effect, and tactics are normal F-star programs in this effect, and having access to, well, to certain primitives that allow them to do things like introspect on F-star terms and kind of mess up with the goal, with the proof goal, like apply a lemma or this kind of stuff. And yeah, this is how it looks in Emacs. This is how it looks in Emacs. If you do an animated GIF and include it in your style, you get to see the various proof goals as you go through them. It's not as interactive as in Coq. It doesn't block in the middle of things, but it records a trace of what the proof goal was at every single bind, basically, of that monad. And you can still see what's happening, or you can add something. I didn't show this dump. You can do some sort of printf debugging. You can say, give me the proof goal at that point in the proof, and then you get it. So what you can do with this? Well, you can use it to discharge verification conditions that otherwise would go to SMT. This is a very, very simple one, basic logic. It's a simple tactic that solves it and solves it completely. What you can do, which is maybe more interesting, is you can basically complement the SMT solver. This is way too complicated and small to read. You don't have to. But this is a proof of this poly MAC, or what is it? Crypto primitive, which works with strange polynomials and whatnot. And it's highly nonlinear arithmetic. And doing this kind of proofs with just the SMT solver is very tricky. What usually ends up happening is that you're going to completely disable support for nonlinear arithmetic because it's way too unpredictable. And you're going to apply lemmas by hand, usually that are lemmas like associativity and distributivity in the dozens. And you can imagine that this is super painful to do. And you have to do that in a prover like Daphne or Y3 or provers that don't, well, maybe Y3 would just fall back to Coq. But if you don't have a way to fall back to tactics or interactive proof, it would be very hard to do just with the SMT solver. It's very painful. And people have actually gone through that pain when proving this kind of things in Haskell. But now we can tell them, hey, I have a tactic that puts your big polynomial into a, how do you say, a form, a sum of products form, and sorts the sums and the products. And then feeds it still to the SMT solver with nonlinear arithmetic disabled, and then the SMT solver can deal with it in no time, because it becomes trivial to prove as soon as you apply all the distributivity and commutativity, right? Those were the silly lemma you had to apply by hand before. So this is something we've used it. And the other we've used it for is synthesizing of star terms. It's again quite small to see, but there is an inductive type which is a bit fancy, but not too much. And you have a tactic called make printer that gives you a printer for this inductive. And it's written in F star and produces code that with Victor's nice pretty printer also looks reasonably nicely indented at least. So in general, we've used these tactics for things like nonlinear arithmetic, so for proof automation, also for bit vectors. So there is a tactic that kind of switches the representation of bit vectors between arrays of bits and, say, native SMT bit vectors. And this can be done with the tactic. And this verified assembly language tool Veil uses that to make use of the SMT solver's bit vectors. We have separation logic, a very simple experiment in which we show that we can do the framing in separation logic using tactics and a similar kind of associativity, commutativity reasoning on the separating star, and then still leave everything to the SMT in the end. So not have to solve everything with tactics, but just the things that are hard for the SMT solver. Because for the framing, basically on each step, the SMT solver would have to figure out a heap and how to split up a heap into pieces. The tactic can give it that. Because it's hard for the SMT, that would be hard for the SMT solver, because the encoding of heaps and whatnot below is higher order. So it's hard for it to reason about higher order stuff. But it's very easy for a tactic to do it using just syntactic matching and certain heuristics. And then, well, leave the rest to the SMT solver. What we've done also is the pattern matcher. So, well, this kind of fancy pattern matching like in LTAC, in Coq, we can implement it as a completely user space tactic that gives you pattern matching on goals and this kind of fancy kind of pattern matching you have like in LTAC. And another thing, I mean, I showed this very simple parser and pretty printer. Actually, we can use tactic to generate low-level parsers and printers that are extremely efficient, that work in place. So a parser that you give it the network buffer, maybe even coming from the network card, right? That where you have a network packet, which might be might contain a TLS payload, and this thing is going to in place basically check that this thing is a well-formed message, and then kind of give you pointers into it without doing any copying whatsoever. And the same thing, well, for printing, well, basically just putting it into the network card buffer without doing any additional copies than the one into the final destination. So this is very cool. In fact, there is even Nadim even built a RFC reader in which you can get those grammars. So the grammars are built with parser combinators. You can get the grammars directly from the RFCs, and then, well, get all the way from the grammars written by people by hand in RFCs to efficient parsers and printers that come with correctness proofs. So that are guaranteed that if they say yes, this is a parsable thing, that there actually exists a parse. So there is also a parser produced at some point, but it's only used for specification. The real thing never produces an AST or any kind of intermediate representation. It just gives you some pointers into a big blob of bytes. So this is quite cool, and yeah, it all uses meta programming to produce the code and the proofs that come with it. So, questions about tactics? Before I show you some details on how some things are done, how we do the weakest preconditions, or do you even want to see this? I'm not sure how we're doing on time, but okay. So then, this is trying to explain to you briefly how a star works under the hood, how it computes its weakest preconditions. So I showed you this pure with capital P, but the rest lowercase, which takes a pre and post condition. In fact, it desugars to something even more primitive, which is this pure with all caps, which only takes one thing, which is a predicate transformer, something that given a post condition, given any post condition that you receive as input, computes the weakest precondition for that post condition. So if you want, okay, we wrote, well, you can write factorial like this. It takes a natural number and returns a natural number. In fact, under the hood, it gets desugared to something like this. Give me what post condition you want to prove. Your precondition then is that the x you have in it has to be larger than 0, and the post condition, well, can assume that y is greater than 0. So it's a bit of a awkward encoding, but it's the way these kind of tools work better to be able to really compute the strongest specification of a program, and then compare it against what the user wrote.
So it should be capital PU on the last line.
Oh yeah, yes. Sorry. And there is a similar thing. For state. I don't think I want to go into the details, but say an increment that you write like we wrote before. Well, in the end, the computed weakest precondition is going to look something like that. Give me the post condition and the initial state. The precondition is, well, applying the post condition to the n+1 because that's what incre computes. So it's I don't think the details are too important. What's more interesting is how this really works under the hood. Because I mean, incre, after the kind of desugaring I explained to you, is, well, get the state, call it x, and then put x+1 back in with a bind in between. And in fact, the way we compute the weakest precondition of incre is really by type inference. So by type inference, where get, put, and bind have these types. So they have, first, the basic types you could imagine, get unit to nat and nat to unit and stuff. The basic types are the same. However, at the specification level, well, get is specified by something called getWp, put is specified by something called putWp, and bind is specified by something called bindWp. Okay, so I just gave names to things. But once you have a specification like this, you can really apply just basic type inference. You can apply type inference looking at this code, and you're going to get a specification like that. Which, if you look at it close enough, this is the same thing. Just I've added instead of doing a bind there, I'm doing a bindWp. Instead of doing a get, I'm doing a getWp. And at the end, I'm doing a pure WP. So in a way, the type inference is very simple. It just kind of falls back to computing that. Now, you need to know what bindWp, getWp, and putWp are so that then you can compute and get the final result, which is what I claimed it would be as a weakest precondition. And well, in order to compute, you need to know what this bind get, what these things are. But yeah, we have this generic way to compute weakest preconditions, provided we know what this bind WP, get WP, and put WP are. And what they are is they're also a monad. They're a monad that lives one level up at the weakest precondition level. I mean, you saw that there is the bind and the return, and the same actions as down. Its type is, well, a bit fancy, but it's a transformer between, well, post conditions and preconditions. Also, that shouldn't be surprising. And if you squint enough, you are even able to inhabit these types. And for a while, that's what we were doing, but it's quite tricky. So I'm not saying that's the right way to do it. In particular, because, well, you're kind of thinking in CPS style, and there are very strong obligations that come with it. If you get this code wrong, I mean, you're going to compute bogus stuff, right? Even if the types guide you, you might still get it wrong. In particular, I mean, this has to match the underlying monad you wrote. It has to satisfy the monad laws and various other conditions on this code. So we no longer write this code by hand. And by the way, we call this thing a Dijkstra monad. It's a monad at the predicate transformer level. So we no longer write these Dijkstra monads by hand. We now generate them automatically. And the main idea is very simple and nice, and I'm going to explain it. So if you look at this predicate transformer for state, that used to look like that, and you just do a bit of massaging and bring these arguments forward, but that's not a big thing, you might notice a certain something to type. And this screams as continuations, and it's the continuation monad. And in fact, you can obtain this state predicate transformer monad automatically by applying the state monad transformer to the continuation monad with result type. So just to unfold this, the state monad is just the one that passes the state around, right? It gives you the result and the final state, provided you pass it the initial state. And this is just the normal state monad transformer, in which you say, well, you're applying state to some other underlying monad. And if you choose this underlying monad to be continuations, you get exactly that. And it's easy. It's automatic. You don't have to guess what is the Dijkstra monad corresponding to it. It's just the state monad transformer applied to continuations. And for any monad that can be written as a monad transformer, you can do the same trick. So this works well for state, exceptions, continuations. It's themselves. You can apply continuation monad to that continuation monad. and you get a weakest precondition calculus for it, for free. That's the for free part, right? Automatically. And not just automatically in terms of code, also automatically in terms of all the proof obligations that you would have to do otherwise. So this is the cool part. We have this way to verify programs that works for a large class of effects, and you just have to give me the underlying monad, and maybe as a monad transformer. And then I can give you a weakest precondition calculus that works for it. In particular, for instance, take the tactics. Now, if you want to verify a tactic, I don't know for what reason, but you can do it because it has an underlying monadic structure. And as long as it doesn't use this magic primitive like quote and whatever, for which you would need to come up also with a specification. If you just say uses just state and exceptions, to do, I don't know, an SMT solver or whatever, you can verify it. And you just get it for free. You don't have to do anything other than write that monadic representation. Well, okay, just to wrap up, what I'm working on at the moment is, well, this tactic framework is still a bit experimental. I mean, it works, and we've even done quite some large things with it, but it was us. And before we kind of inflict it on users, I think it needs maybe a bit more documentation and maybe better error messages and the usual kind of things. Then we are working on an extension of this Dijkstra monad for free idea I showed you just on the last slide, in which you can even go beyond what you can directly express as a monad as the same monad transformer applied to the continuation monad. You can in fact swap in a different monad transformer that's independent from the one that expresses your effect, provided you can kind of produce some sort of lifting between the, which is usually called the monad morphism, between the underlying monad at the expression level to this monad at the specification level. So there is something more, and if you want to do effects like non-determinism or probabilities, or which is the next thing on my list, then it seems you need that. So those are also effects we would like to look at. So we're looking at, well, how we can extend the effects for which we can do these Dijkstra monad tricks. Then another thing we would like is, I mean, currently the effect system of F-star is syntactic. So say if a piece of code ever throws exceptions, even if it catches them, all of them, it's still in the exception monad. Similarly, if a piece of code internally uses state, but externally behaves functionally, it's in the state monad. However, we would like to be able to say, hey, it behaves functionally, so it should be a function. It should lose certain effects it has. And this is quite tricky. So we have, I mean, for exceptions and state, we have some ideas, but how to do this in a general way that would work for a large class of effects, that's tricky. And then, well, there's still work on so we've done some meta theory work for small fragments of F-star, but we still don't have anything like a complete meta theory. In the end, the pipe dream is to have even a verified type checker, because the type checker of F-star is written in F-star. There was a previous version of F-star for which they pulled this through by kind of going through Coq, and they claimed they produced the largest Coq certificate ever produced. They needed to run on a cluster for many weeks to check that certificate. That was like gigabytes long. But that was for a much simpler system. That was like that was a variant of F-star that didn't really have dependent types, or not the most general kind. And so now the system is more powerful. So the meta theory is trickier, and well, then relating this meta theory to the actual implementation would be quite some work. But the fact that it's written in F-star, well, gives us hope that we can at least check some properties of the actual type checker. Maybe it's not that it's sound, or that would be funny because it would prove that it's unsound. But say that it doesn't cause. It has a name in F-star, like the kind of assertion failures that this should have never happened. Like the type checker blows up in your face saying file a bug, yeah, because in a way it reaches a place in which there is some pattern match where you think that code should be dead and never be reached, and it is. So, for instance, those kind of weaker property we could hope to prove for the actual type checker even now, if someone would have the time to do it. Yeah. So just to wrap up, so F-star is this verification system for effectful programs. It's a functional programming language with effects. is a program verifier based on weakest preconditions and SMT. And when all this fails, you have the full of dependent type theory to do your proofs by hand. Now you even have tactics. It's open source on GitHub, developed in the open. You can send us pull requests or at least bug issue. You can file issues. There's tutorials and papers and the slides, including these ones. I'll put them on the website.
Thank you.
Questions?
Yes. So you say that once you're in the exception effect, you will always be in the exception. So you mean you don't have handlers for your effects? You don't have handlers?
Handlers. No, not really. I mean, we really are based just on monads. So I think, well, one thing you could do to implement something like a handler would be to expose the monadic representation, right? To expose the fact that exceptions are just the option monad, and then to prove that, hey, you are not returning none, but in a way about the reification of of your computation. What I mean by reification, the underlying monadic representation. You can do this. You can prove after the fact that your thing doesn't return none. The thing you cannot do is say, because you've proved that, you're now able to really go down in the effect lattice and now have a pure computation. And in a way, I mean, it's not like the feature would be hard to add. The question is, when is it sound, and and what was the theory that justifies it? I mean, at least for exceptions, it seems easy, and it seems naturally sound. But say you do the same thing for state, then it becomes a lot trickier. Like you have to talk about, well, did your code allocate? Is that still pure? Even if internally it behaves like a function. How do you really justify the fact that you can forget about its internal effects? So it's actually tricky to justify at the theoretical level. And yeah, with respect to handlers, yeah, what we're doing at the moment is really just monads. It would be nice to have something like algebraic effects, but I don't know how to compute weakest preconditions for algebraic effects and this kind of stuff. So I would say it's a bit further. It's a bit further out. We would first have to understand how to do all the things we're doing for monads in that quite different setting.
Yeah, because I think you can't have a direct effect for divergence, for instance. What's the handler for divergence?
Yes. And you could say yes.
More questions? Yes, perhaps one more. Stepping back, how do you see the evolution of F-star with respect to COP, which is already there and successful, as you mentioned earlier? I mean, it doesn't need to be a competition, but what your team behind F-star see in the future in terms of market shares without competition? I don't know. What would be, or practically reversely? I mean, conversely, if you have to sell F-star but to engineers who are, I don't know, discriminating hackers, perhaps they have a PhD as well, but they don't know which way to go.
Well, I think for people who are successfully and happily using Coq, I think they should just keep doing that. I think and in fact, I mean, we've also, for some other projects I'm doing, including the one Marco work on, we were using Coq, and it's just fine. I don't feel bad about it. It's very good at what it does. At the same time, as you were saying, if you're trying to target engineers, telling them that, oh, you have to give up on all your effects, or you have to go, well, encode them as monads and try to do some of this stuff. But in Coq, it's not the same kind of sale, right? I think the main selling point of F-star is the fact that you have all of ML, including the effects, that you have ways of adding new effects as you wish, and that you get these weakest preconditions computed for you for whatever effects you have around, and a nice encoding to an SMT solver with which that works, well, most of the time. And then, well, for us, the kind of that we can also do interactive proofs is like, yes, when the SMT solver doesn't work, that's our way of doing interactive proofs, and it's not the first thing we would try.